often about earthquakes and wildfires, but this morning it's another natural threat.
Northern California volcanoes are no longer considered a threat. The U.S. Geological Survey has updated its risk assessment.
Molten rock has been moving beneath the surface of Northern California in ways that were once invisible to science, but new high-resolution geophysical scans have revealed an unsettling truth. Mount Shasta, the snow-capped giant of the southern Cascade Range, is connected to a deep and extensive magma system stretching westward toward the offshore Cascadia Subduction Zone. The findings came after a team of geologists used advanced seismic imaging, electromagnetic conductivity mapping, and crustal tomography to look beneath the volcano's roots. What they discovered was not a simple, isolated magma chamber, but a vast branching network of molten and semi-molten rock that appears to interface with fault structures directly linked to the Cascadia megathrust, a tectonic plate boundary already known for its potential to unleash one of the most destructive earthquakes and tsunamis in North America. The revelation was significant enough that the U.S. Geological Survey and state emergency agencies issued a rare red alert advisory for geological monitoring, signaling that conditions warrant the highest level of scientific attention and public readiness. Before we start, smash the like and subscribe buttons for more updates. Mount Shasta has long been recognized as a stratovolcano with a violent geological history. Its slopes layered with the remains of explosive eruptions, pyroclastic flows, and lahars that have rolled across valleys in the not-so-distant past. But until now, most volcanologists treated it as a relatively independent system within the Cascade Arc, drawing its magma primarily from localized mantle plumes and crustal melting zones. The new data show that this is a partial truth at best. The imaging suggests that deep feeder channels from the mantle wedge beneath the Cascadia Subduction Zone extend inland, branching under the Klamath Mountains and connecting with Mount Shasta's magma reservoirs. In simpler terms, the volcano and the subduction fault are not two separate hazards. They are linked parts of a single dynamic geological machine. This means that changes in one could potentially influence the other in ways that were not fully appreciated before. The Cascadia Subduction Zone, stretching from Northern California up through Oregon, Washington, and into British Columbia, is already infamous among geologists. It marks the boundary where the Juan de Fuca Plate is diving beneath the North American Plate, storing vast amounts of strain over centuries until it releases in colossal earthquakes. The last such full-margin rupture occurred in January of 1700, producing a magnitude 9 event and sending a tsunami across the Pacific to Japan. Since then, smaller segments have slipped, but the southern portion, nearest Mount Shasta, has been relatively quiet. The new evidence that molten rock from the subduction process is actively feeding and interacting with Shasta's system adds a new dimension to the hazard landscape. The same tectonic forces that could trigger a Cascadia megathrust quake may also be capable of pressurizing Shasta's magma network, potentially increasing the likelihood of volcanic unrest in concert with seismic events. This hidden connection was detected using an array of temporary and permanent seismic stations placed across Northern California and Southern Oregon, combined with magnetotelluric surveys that measure variations in the Earth's natural electromagnetic fields. Molten rock conducts electricity differently from solid rock, and the patterns that emerged from the data revealed elongated, branching anomalies running diagonally from the coast inland toward Shasta. Follow-up seismic tomography confirmed that these anomalies were low-velocity zones, another hallmark of partially molten material. The anomalies were not random. They aligned closely with mapped fault traces and deep crustal fractures, suggesting that they form a natural conduit for magma movement. By modeling the thermal and mechanical behavior of these pathways, the research team concluded that they could act as pressure transfer systems between the deep Cascadia melt zones and Shasta's upper crustal magma bodies. For years, volcanic hazard models have treated Mount Shasta's eruption scenarios as largely independent of Cascadia's megathrust cycles. The standard assumption was that the timescales of tectonic stress accumulation and magmatic recharge were different enough to make direct triggering unlikely. But the discovery of a connected magma fault system undermines that separation. If the Cascadia Fault were to rupture, the rapid redistribution of stress in the crust, combined with possible decompression of deep melt zones, could send pulses of magma toward the surface beneath Shasta. Even without a megathrust earthquake, slow slip events, the kind that occur over days or weeks without generating large seismic waves, might subtly pressurize Shasta's plumbing, edging it toward instability. The reverse is also possible. Significant magmatic movement beneath Shasta could add stress to nearby segments of the fault, potentially hastening their failure. The red alert designation in this context is not a prediction of imminent eruption, but rather a call for maximum readiness in monitoring and data collection. It means that instruments will now stream real-time data to analysis centers, satellite thermal imaging will be updated more frequently, and airborne gas surveys will be flown over Shasta to detect changes in volcanic emissions. The key gases, sulfur dioxide, carbon dioxide, and water vapor, can signal shifts in magma movement long before surface deformation is obvious. In addition, GPS arrays around the volcano will measure ground inflation or deflation to the millimeter, offering clues about whether magma is rising or retreating. The linkage to Cascadia means that seismic events along the coast will now be cross-referenced immediately with volcanic data to look for correlated changes. From a geological perspective, this connection is both fascinating and sobering. The Earth's crust in this region is thinner and more fractured than in many volcanic arcs, partly due to the complex interaction of subduction, transform faulting, and crustal accretion from ancient terrains. This patchwork structure creates pathways where magma can migrate far from its point of origin. Beneath Shasta, the upper crust is riddled with intrusions from past eruptions, many of which remain warm enough to remobilize if new melt intrudes. These partially solidified bodies can mix with hotter magma from depth, changing its chemistry and viscosity, and potentially making it more explosive. The interaction with Cascadia's melt zones could accelerate this process by providing periodic injections of fresh basaltic magma, which can heat and pressurize existing reservoirs. Historically, Mount Shasta has erupted multiple times in the last 10,000 years, with its most recent significant activity around 200 to 300 years ago. Some of those eruptions were large enough to send pyroclastic flows tens of kilometers from the summit, obliterating everything in their path. The flanks of the volcano are steep, and glaciers on its upper slopes mean that even small eruptions could generate lahars, fast-moving slurries of mud, ash, and rock, capable of racing down river valleys into populated areas. The new understanding that these events might be tied, however indirectly, to tectonic processes along the Cascadia Fault adds a new layer of urgency to hazard planning. It suggests that communities may need to consider dual event scenarios, where a major earthquake could be followed by or even coincide with volcanic unrest. This interconnected hazard model is not without precedent. In other subduction zones around the world, such as Japan's Nankai Trough and certain segments of the Andes, large earthquakes have been followed by volcanic activity months or years later. The mechanisms vary, but they often involve changes in crustal stress, fluid migration, and decompression melting triggered by the quake. What makes the Mount Shasta-Cascadia link unusual is the apparent physical continuity of the magma system, which could make the interaction more direct. While the geological timescales for such processes are still long compared to human perception, the presence of an active connection means that each major tectonic or magmatic event in the region must now be evaluated in a broader, integrated context. The geologists involved in the discovery emphasize that the red alert is not cause for panic, but for preparedness. The goal is to collect as much high-quality data as possible while the system is still in what appears to be a stable state, so that if changes occur, they can be detected early. This includes refining models of how magma moves through the connected pathways, estimating the time it might take for deep pulses of melt to reach eruptible levels, and understanding how fault slip could influence this movement. It also means revisiting historical records, including indigenous oral histories, to look for patterns of coinciding seismic and volcanic events that might offer clues to the system's behavior. Mount Shasta's prominence on the landscape has always made it a subject of fascination, both scientifically and culturally. It rises over 14,000 feet, visible from more than 100 miles away on clear days, and dominates the local climate and hydrology. Snowmelt from its slopes feeds major rivers, and its volcanic soils support diverse ecosystems and agriculture. Any significant change in its activity would have far-reaching environmental and economic impacts. The red alert status now underscores that these impacts cannot be considered in isolation from the seismic risks of the Cascadia Subduction Zone. Planners and scientists alike must now envision scenarios where a single geophysical chain reaction could disrupt both coastal and inland regions simultaneously. The discovery also raises broader questions about how many other volcanic systems might be more connected to tectonic boundaries than previously assumed. Advances in imaging technology are continually revealing that the Earth's interior is more fluid and interconnected than the simple textbook diagrams of isolated magma chambers suggest. For hazard assessment, this means that interdisciplinary monitoring, combining volcanology, seismology, and geodesy, will be increasingly important. The Mount Shasta Cascadia link could serve as a case study for integrated hazard forecasting, where the interplay of different geological processes is modeled in real time. In the weeks and months ahead, the expanded monitoring effort will likely produce a flood of new data. Every microquake, every subtle change in gas output, every fractional shift in ground level will be logged, analyzed, and compared against baseline conditions. The challenge will be distinguishing normal background variations from signals that truly indicate a shift toward instability. Given the stakes, a system that could involve both a megathrust earthquake and a major volcanic eruption, the margin for error in interpretation is thin. Scientists will have to balance the need for caution with the imperative not to overlook early warning signs. Even without immediate unrest, the revelation of this hidden magma fault connection changes the narrative of Mount Shasta's role in the regional geologic system. It is no longer just a volcano perched above its own private magma source, but a node in a vast network of molten rock, fractures, and tectonic stress that extends from deep beneath the Pacific Ocean to the snowbound summit. The red alert is a signal that this network is now under the closest possible watch, not because an eruption is certain, but because the underlying dynamics are more complex and potentially more hazardous than anyone realized before the data brought them to light. Beneath the rugged landscapes of Northern California, the revelation of Mount Shasta's hidden connection to the Cascadia Subduction Zone is forcing a deeper investigation into the processes driving this unusual geological system. While the initial discovery focused on mapping the molten pathways, scientists are now turning to the mechanics of how such a vast subsurface network formed in the first place. This requires looking back millions of years into the region's tectonic evolution, when the collision and accretion of ancient oceanic terrains welded a patchwork of crust onto the western edge of North America. These events left behind a legacy of deep faults, sheared metamorphic belts, and varying rock densities, an irregular architecture that has proven ideal for channeling magma far from its point of origin. In Shasta's case, this means melt generated by the subduction of the Juan de Fuca plate doesn't simply rise vertically to create a volcanic arc. Instead, it follows oblique fractures inland, linking coastal magma sources to a volcano more than 100 miles from the trench. This architectural complexity means that the magma beneath Shasta is chemically diverse. Samples from past eruptions show a mixture of basalt, andesite, and dacite compositions, suggesting that the incoming melt from the subduction zone interacts with older, cooler intrusions in the crust. Over thousands of years, repeated injections of hot magma can cause partial melting of these pre-existing bodies, producing hybrid magmas that are often more viscous and gas-rich. These hybrid compositions are particularly dangerous because their increased viscosity traps volatile gases until pressure builds to explosive levels. The Cascadia linkage may introduce fresh pulses of basaltic magma more frequently than previously assumed, creating periodic rejuvenation events that re-energize Shasta's system. The physical linkage between Shasta's magma reservoirs and the deeper Cascadia melt zones also changes how stress is distributed underground. When the subduction zone experiences even small episodes of movement, such as slow slip events, the pressure can be transmitted through these connected pathways. This mechanical connection could subtly deform the walls of Shasta's magma chambers, allowing cracks to open or seal depending on the direction of stress transfer. Such deformation doesn't always result in visible surface changes, but it can alter the dynamics inside the magma reservoir, potentially accelerating crystal settling gas exsolution, or mixing between different magma layers. These internal changes can transform a relatively stable magma body into one that is far closer to eruption conditions. From a geophysical monitoring standpoint, the implications are profound. It means that the health of Shasta's system can no longer be assessed in isolation from the seismic state of the Cascadia Subduction Zone. A quake off the Oregon coast, for example, could produce subtle seismic waves and stress changes that ripple through the deep crust toward Shasta, altering magma behavior in ways detectable only through careful, synchronized monitoring. This has led to proposals for a unified Cascadia Shasta hazard network, where seismic, volcanic, and geodetic data are processed in real time by integrated modeling systems. Such an approach would allow scientists to detect correlations between tectonic and magmatic activity that would otherwise be missed by siloed monitoring programs. Another avenue of research emerging from this discovery involves fluid migration. Subduction zones are notorious for releasing superheated water and carbon dioxide from the descending oceanic plate, and these fluids can migrate great distances through the crust. In the context of the Shasta-Cascadia connection, such fluids may not only contribute to magma generation, but also lubricate fault zones, altering their frictional properties. This creates the possibility of a feedback loop. Fault slip can drive magma movement, and magma movement, by heating and pressurizing fluids, can influence fault behavior. The challenge is that these interactions occur over a wide range of timescales, from seconds to decades, and may involve processes too deep to be directly observed. Researchers must rely on indirect signals such as gas chemistry at fumaroles, microseismic patterns, and changes in crustal conductivity to piece together the full picture. The structural continuity between Shasta and the Cascadia Subduction Zone also forces a re-evaluation of volcanic hazard mapping in Northern California. Traditional hazard maps around Shasta have been drawn based on topographic pathways for lahars, ash dispersal patterns from past eruptions, and the reach of pyroclastic flows. These maps assume that the volcano's behavior is primarily influenced by its own internal cycles, but if coastal tectonic events can influence eruption timing, then hazard planning must account for scenarios where evacuation routes, communication systems, and emergency resources are already strained by an ongoing megathrust earthquake response. Such compound disaster planning is rare in the United States, but has precedent in other parts of the world, such as Indonesia and Chile, where volcanic and seismic hazards are intertwined. At the scale of the deep Earth, the connection between Shasta and Cascadia highlights the role of mantle wedge dynamics. Above every subduction zone lies a wedge-shaped portion of mantle that is partially melted by fluids released from the downgoing plate. In most cases, the magma generated here rises to form a volcanic front relatively close to the trench. In the Shasta segment, however, the mantle wedge appears to be unusually hot and broad, allowing melt to travel laterally as well as vertically. This lateral movement explains why the Cascade Arc in Northern California includes not just Shasta, but also other volcanic centers such as Medicine Lake Volcano, which may also be part of the same extended magmatic system. The idea of a shared plumbing network among multiple volcanoes adds further complexity, since activity at one center could potentially influence the others. While the public's attention naturally gravitates toward the potential for eruptions, scientists are equally concerned about what this discovery means for understanding crustal heat flow and long-term landscape evolution. The intrusion of magma into the crust changes its thermal structure, influencing everything from groundwater circulation to the stability of rock slopes. In areas around Shasta, elevated heat flow has been measured in geothermal springs and wells, and the new linkage model suggests that these anomalies could extend much farther than mapped. Over centuries, persistent magmatic heat can weaken bedrock, alter mineral compositions, and even affect erosion rates. Subtle but important processes that shape the surface environment. The red alert status has also galvanized the use of cutting-edge technology to explore the system further. One particularly promising method is ambient noise interferometry, which uses background seismic hum to detect tiny changes in the crust's properties. Because the magma pathways between Shasta and Cascadia are now suspected to be semi-permanent features, any change in their temperature, pressure, or melt content could alter how seismic waves pass through them. By monitoring these changes continuously, scientists can build a kind of stethoscope for the deep Earth, listening for the earliest signs of instability. Drones equipped with spectrometers are also being deployed to survey gas emissions over Shasta's flanks, capturing high-resolution chemical fingerprints that can be matched to specific magma sources. If the Cascadia linkage accelerates this ascent, it could mean that warning times for future eruptions are shorter than currently assumed. This has significant implications for evacuation planning, as communities around Shasta might have less than a week, or in some scenarios just a few days, to respond. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Mount Shasta's magma link to Cascadia Fault? Will it erupt? We want to hear from you. Thank you for watching and see you next time.